Let's do another video, and let's start off with a nice easy one now that we've all talked about other things. You just had to be there. What's the square root of 16?
8. Oh, no, sorry. 4.
We're going to go with the correct answer, which is 4.
Sorry.
Do y'all agree with that?
Yes.
Of course you do. I'm the one writing the answer, so it has to be right.
Sorry.
The square root of 18. Do it again.
No. That's not right.
What? Wait. Do I divide by the index? What things will I divide by the index?
Exponent.
The exponents. Is this an exponent?
No.
Then you better not be dividing by the index. What we need to talk about now, in case you hear a donk sound, that's someone dropping their pencil over and over again. It's not my fault.
I'm sorry. I'm so sorry.
She has apologized. Will you forgive her? I do.
Can you stop talking into the mic like
No, I cannot stop talking into the mic. It's what I do. I'm creepy.
that? Oh my god.
Side nose.
Anybody who ever wanted to be a teacher, watch these videos. If you think you can handle this, sure, go into teaching. If it's too hot to handle and too cold to hold, then maybe you shouldn't do it. Product rule for radicals. This is what you're going to see. The nth root of A times the nth root of B. When you're multiplying radicals and you have the same index, this is very important here. You must have the same index. When you have the same index, you can combine this into one larger radical that has the product of these other radicands, A times B. You may be wondering, how does this help me in this problem? Well, when I look at the square root of 18, I can see this guy as the square root of 9 times 2. Do you agree? Now, this product rule can be combined as one, but it can also be split up. Do you believe me? Okay, you don't believe me. Take this example. This is something that we did last week, and you guys never gave me any issues about this. If I say the square root of 25x to the 8th, without writing it, but just by thinking it, you would have done this in your mind. The square root of 25 times the square root of x to the 8th. You didn't even write that, but you just wrote the answer as 5x to the 4th. That's what you did. You used the product rule, even though we hadn't really officially talked about it. You used the product rule to take the square root of each piece in that product, right? Same thing over here with the square root of 18. I can split this up and say the square root of 9 times the square root of 2. What's the purpose of me splitting that up?
Because that's what the rule tells us to do.
It's what the rule tells us to do, but what's the purpose? What do I get out of it? You guys typically don't ever do anything unless you get something out of it.
A whole number? A real number?
Well, these are all real numbers. They may not be nice decimals, but they are real numbers. That's going to change at the end of this chapter, though. What's the square root of 9? That's where we can be happy. It's just 3, right? But the square root of 2 must stay as the square root of 2, because he's not a perfect square, is he?
No.
Trust me, I know a lot about perfect squares, right? Now, make sure you do read these answers correctly. This would be read as 3 square roots of 2. You read this as 3 square roots of 2. Please don't say 3 root 2, because you just look like a fool. Okay? It bothers me tremendously.
Well, we're not going to say it. We're going to write it,
3
right?
times the square root?
You may say 3 times the square root of 2. You may say 3 square roots of 2. And sometimes we'll say 3 times, especially when things get much more complicated. Because what we're seeing today, these guys are nice, simple guys. Just like this next example here. If I take the square root of 75, you're going to treat this guy just like you did the square root of 18. you want to see if there's a perfect square that's a factor of that. And if you can't see that, then we'll talk about a systematic approach for breaking this 75 down completely. But I think you guys can see a way to break this down, right? This is 25 times 3, right? Why did I want to separate it and look at it as 25 times 3?
It's easier.
So it doesn't matter what two numbers you use that multiply 25 numbers? Or
It doesn't, but you're going to have to find, since this is a square root, you'll need to find a perfect square.
At least one, right?
So it's 5.
Right, because here's what you could have done. You could have done 5 and 15. But 5 times 15 doesn't help me. But 25 does, because this guy right here is a perfect square. And what's the square root of 25?
So it's 5 square root of 3.
Right, and 3 is this lonely guy who's not a perfect square, and he stays inside. Do y'all agree?
Oh, okay, so the whole point is you want to find the number that you're multiplying with. One of them needs to be a perfect.
You need to find perfect squares or perfect powers. If I do a cube root, which I'll do later, you have to find a perfect cube. If I'm dealing with the fourth root, you have to find something that's a perfect fourth power. Now, let me show you another way for breaking this guy down. You guys remember doing factor trees back in the day? Factor trees always made me happy. When you do a factor tree, I'm going to show you a very systematic way of breaking this down. To do a factor tree, you look at prime factors. What's the first prime number that we have? No.
5,
2.
7, 2.
2 is the first prime number, right? But does 2 go into 75?
No.
No, because you're going to go through this systematically. What's the next prime number? 3. Does 3 go into 75? 3 goes into 75 25 times. I'm going to lightly cross out the 75 so I don't get confused with them later on. Now, does 3 go into 25? So what's your next prime number after 3?
5.
So does 5 go into 25? Yes, 5 goes in here 5 times. So I'm using prime factors to break this down. And the numbers you see on the outside make up what we call our prime factorization. That means 75 broken down into its most basic components breaks down as 3 times 5 times 5. Do y'all agree? Now you need to find a perfect square. A perfect square can be something like the 25 we found up here, but if I'm writing out the list of factors, a perfect square is going to be found by finding 2 of the same factor. I've got 2 5s inside here, so that means I've got 5 squared, right?
Right.
Serenity now. So that means when I have this inside the square root, I end up with a 5. So this guy contributes a 5 on the outside. With the square root, it takes 2 of one factor to give you 1 of them on the outside. If it were a cube root, you'd have to have what? 3 factors on the inside to give you 1 of those outside the radical. So this is 5 times what? What was left inside the square root?
3.
So it's still the same answer that we had before. You guys with me on that?
I mean, like you was just showing us that for like a different way, or
It's a different way of doing it. Because suppose you didn't see that 25 went into 75. You'd have to break it down another way. Now for me, since I'm making up these problems, I know what the answers are going to be, and I know what the perfect squares are. But if you're not used to seeing those perfect squares, you break it down using a factor tree.
perfect.
Let's do the square root of 700. Now there's a very easy way to break this down, and it's really easy if you keep your mind on your money and your money on your mind, right? You talk about your bills, you talk about your Benjamins, because what's an easy way to look at 700? It's 7 times 100, right? Now why is that useful for me to write 7 times 100?
Because 100 is
100 is my perfect square,
square.
and what does he become on the outside?
Root.
He becomes a 10, and you're left with the 7 inside the square root. Do you agree?
I think that's just better to do instead of the factor tree. I don't like it.
Well, that's because I gave you something that was easy to see. That was 7 times 100. It's not always going to be that way, so you're going to have to break it down piece by piece. Like if I say the square root of 147.
Well, the 7 tells you it's odd, right?
So what?
Can I tell you anything?
Doesn't tell you what goes into it.
It's not gonna be a perfect square, is it?
Nope.
So that's why we know.
But you're going to have to break it down. The thing is, how do you break it down? And that's what I want to show you with this guy. Let's look at 700. If I have the square root of 700, I'm going to break this down using a factor tree. If you don't see the perfect square factor that goes into it. If you've got a calculator, you break this down and you know your primes. The first prime number I have is 2. Does 2 go into 700?
Yes.
How many times does 2 go into 700?
350.
350 times. Keep using the 2 until it doesn't work anymore. Does 2 go into 350?
Yes.
How many times?
175.
175. Does 2 go into 175? No, so you're done with that guy. Does 3 go into 175?
Yes.
No. What is the sum of the digits of 175?
Oh,
What's 1 plus 7 plus 5?
12.
It's 13. Does 3 go into 13 evenly? Then 3 does not go into 175 evenly. So ditch 3. 3 doesn't work. Does 5 go in here?
Yes.
How many times does 5 go in here?
A lot.
I'll help you out. It's 35 times. See, if you had a calculator, if you were relying on that, you could easily take care of that. Does 5 go into 35? You keep using it.
Yes.
It goes in 7 times. Here is your prime factorization. Since we're dealing with the square root, we have to have how many of the same factor? 2. Look what I have. I have a pair of 2's and I have a pair of 5's. Do y'all agree?
Yeah.
Notice, what mathematical operation did I use when I broke down the 700? All of this is in terms of what? Multiplication, right? I rewrote 700 using multiplication. Do you agree? That means that anything that gets pulled out of this guy, so having a pair of 2's inside gives me 1 2 on the outside. Having a pair of 5's gives me 1 5 on the outside. What goes in between the 2 and the 5?
Multiplication.
Since all of this was multiplication, this is multiplication. And that's multiplication times what was left inside the radical. This was the lone guy left inside, right? Would you leave your answer like this?
No.
You'd finish and you would say 10 square roots of 7. So yeah, this took a long time to do it, but if you didn't see 7 times 100, this is another way of going about it.